Now we're going to take a step back to cover some of the fundamentals that's going to help us to get to these more involved topics of, say, standardization. And we're going to talk here for the next few minutes about electrical waveforms that your units output, and also a bit about their fish catching attributes as well. So we'll get into it right now. So there's three main types of electrical waveforms we're talking about. The first is direct current, DC. It's also called continuous DC or smooth DC. The second type is the most common type that's used in electrofishing, pulse direct current. Many forms of that. And finally, the last one, alternating current, AC, the type of current that comes out of your wall sockets in your house. And actually there are many forms of this. Out of your wall socket, there's just one form, but electrofishing equipment output many forms. So the first one is direct current, and direct current starts at a point in time and then continues in a smooth way. One second, we'll find my mouse. Okay, got it. All right, so basically this is an oscilloscope tracing where we have volts on the y-axis and time on the x-axis, time in milliseconds. And basically, if you're using DC, you flip the switch on, the voltage goes up to some level that you set, and then just continues that voltage level. So for DC, average voltage, if you want to think of that, it's the same thing as peak voltage. Average amperage, same thing as peak amperage. Average power, same thing as peak power. So it's pretty simple in that way. So advantages of continuous DC is typically it causes attraction of fish to the anode, and that can be very dramatic. It's also often less injurious, especially with trout and salmon. So it's used, if it's the first waveform of choice with trout and salmon, if they can use it, that's DC is what's used. So here's a oscilloscope tracing again, and you'll see here that we have a grid, which is what an oscilloscope shot looks like, or a scope meter. And in this case, every vertical division is set at 50 volts per division. So that's the 0 volt line, or that's the 0 volt line, I should say, denoted by that black rectangle. So each division is 50, so it's 50 volts, 100 volts, 150, and something 200 right here. The DC waveform is going across like this, so it's something less than 200 volts. And I should say this is 100% duty cycle. That means duty cycle is percent time on, and DC is always on, so 100% duty. Sometimes you get a ripple, what we call a ripple or sawtooth, on top of the DC. And so there are some manufacturers that keep a ripple on their smooth DC because they think that enhances the catchability. But basically what occurs is that, and we'll talk about what rectified AC is later, but AC is input and then converted to this fully rectified AC. It's actually then becomes a DC waveform, and then it's transformed to this profile here, which is the ripple. So that's what you see, kind of a sawtooth DC. Not exactly smooth, so it's sometimes called ripple DC. So what are the drawbacks of DC? Well, DC may require slightly higher amperage. It requires more power than pulse direct current to be successful. And since it's always on, since it's 100% duty, it's also more energy consumptive. So because of that, DC is more restricted in its use for a conductivity range. And for example, in Lake Superior, for successful fishing of those fish assemblages up there, we estimated the conductivity range at about 35 to 320 microsiemens per centimeter when using a two-boom metal hull boat with a infinity control box. So you can see that is a restricted range relative to other waveforms typically. Also, DC is not available in all control box units, backpack or boat. So what are the fish catching considerations? Well, DC is pretty simple. The duty cycle is always 100%, so there's no adjustment there. And the frequency with the pulses per second doesn't apply in this case because it's always on. There's no pulsing. So you're down to adjustments of voltage and amperage. And thus your strategy is simplified really, and to building these volt and amp output goal tables for just this one waveform. So I should mention what is a volt and amp output goal table, and this is something we'll be talking about later in a module about standardization. But here's an example goal table where you have a particular waveform and a particular electrode arrangement. This is for a backpack shocker, so it has ring anode, rat tail cathode. Its resistance at 100 microsiemens per centimeter is 275 ohms. That's kind of an average for backpacks. And we have something called fish conductivity at 115. So that's the criteria. But the table itself, how you read that is when you go out to a site, you read the conductivity and you find of the site, and then you look it up in the table, say it's 75 microsiemens per centimeter, and then you say, well, what's my target peak voltage? 303. And what's my target peak amperage? In this case, 0.82. So you would, if you're just going by voltage, you just go out into the stream and deploy your electrodes in 1.5 feet or 2 feet of water and up the voltage till you came up with about 303 volts. Or do the same thing and watch the ammeter and adjust the voltage so you get about 0.82 amps. So that's an output goal table. We'll talk about that more later, but that just guides you. It's a guidance for your initial settings that you start out with. Okay, that's it for DC. Next one's pulse DC, pulse direct current. And as we see here, here's a graphic of pulse direct current. These are square waves. So the time, as before, the x-axis time, the y-axis of volts. And as you turn the unit on, the pulse is not present, then it becomes present, not present, present, not present, present. So it's pulsed. And there are several attributes about pulse DC. It's much more complicated than DC. So we have some terms here to the right. A pulse, that's a part of the waveform during which voltage is present. So that would be here. A pulse width is the time the pulse is on. So that's the pulse width here. Frequency of the number of pulses per second. So we hear pulses per second. Sometimes it's referred to as hertz. The period is the time from the beginning of one pulse to the beginning of the next pulse. So this period is a period right there, beginning of one pulse to beginning of the next. And a very important concept is duty cycle. And that is the ratio of on time, that is the pulse width, to the period, expressed as a percentage. So let's look at this waveform here. The period is from the start of one waveform to the start of the next, and the pulse width is here. So how much of the period does the pulse width take up? In this case, just eyeballing it, it looks like about half. So that would be a pulse width over a period of about 0.5. And you multiply that by 100, that's 50% duty cycle. And I want to mention about this idea too is, well, let me back up a little bit and just talk about volts here for a second. Now, for fish catching, we're always talking peak. Peak, that's the top of the waveform. That's what fish react to. So whether it's peak voltage in this case, amperage is doing the same thing as voltage. So scope meters measure voltage, but amperage is doing the same thing in the background. So peak volts, up on the top, the waveform, peak amps. That's what fish are reacting to. That's what we're concerned with. That's what we want our meters to be reading as peak volts or peak amps. Now, average voltage or average amperage here is basically the peak times, rather, the peak times the duty cycle. So let's just say the peak is 100 volts and the duty cycle is 50%, then the average would be 50 volts, like that. Now, this is a point of confusion for folks that are changing from a GPP to, say, some other control box that measures peak amperage. And numerous calls to manufacturer on this where they're used to 2 or 3 or 4 amps, and then all of a sudden they're seeing 16 amps on their new machine, and they're thinking they're blowing their machine up. But if at a 25% duty cycle, peak is going to be 4 times average. So on a GPP, you're talking average. And do want to say also that there's a nice blog at electrofishing.net about what your ammeter is telling you. Okay, advantages of pulse direct current. There's many options. So there's many combinations of frequency and duty cycles that you can experiment with to increase your fish catching. It may cause attraction of fish to the anode, but this is not as obvious or is done as effective usually as with just continuous DC. It's much less energy demanding, so pulse direct current can be applied across a broader connectivity range, and it's generally more effective for capturing these smaller individuals, smaller fishes than DC. Okay, so here's an oscilloscope or a scope meter tracing of a pulse direct current waveform, and you can see here that this is about a 25% duty cycle, so the period goes from here to here, and about 25% of this time is taken up by the pulse, so that's about 25%, 24% denoted here. And we got 50 volts per division, so this is the 0 voltage line, so 50, 100, 150, 200, slightly less, than 200. Also, the baseline starts slightly below the grid here, so about 199 peak volts, and that's this denote here, volt peak. This is the effect also, I want to throw this in, that when you load a machine up, and that is when it goes to higher conductivity, that the waveform tends to get spiky. So we just call it a spiked pulse. So this is a LR24 backpack unit, and here you see we're loading it with higher and higher voltages. So here's about 50 volts peak, here's 200 volts peak. The scale has changed, vertical scale has changed, by the way, so be aware of that. There's 10 volts per division on this slide, 50 volts per division there. So anyway, it goes from 50 up to about 637 peak volts being output, and you can see that the waveform starts slanting and becoming spiky, as we call it. So the question is, where do you make that peak voltage determination? And what we say is where the width first becomes about 1 millisecond wide. That's where we call it. That's what we call peak. Here's some more scope meter tracings or graphs of LR24, and these are just different duty cycles. So you can see starting at about 10%, you have narrow pulses, 20%, 30%, on up to 80%. So that's the effective of duty cycle. Now those are square waves we showed you, and we call them square, even though they look like rectangles, we call them square because the corners are squared off. And these are rounded waves that mostly you'll see rounded waves pretty much limited to GPPs and type 6 control boxes, but they're generated from a rectified AC, and so you see this kind of rounded presentation. And how that's done is alternating current is over here, which we haven't talked about quite yet, but it's a sine wave. So just imagine a sine wave, alternating current going through, and pass it through a diode in your control box, and then you get this half wave rectified DC, and that's how the GPPs work for outputting direct current, pulse direct current. Another waveform that is a pulse direct current waveform is something called a gated burst, and this particular waveform deals with packets of pulses. So in this case, there are 4 pulses per packet, and the packets are separated. So the packets come at a low frequency, and the pulses within a packet come at high frequency. So this particular waveform was developed because there was real concern about injury to salmon and trout from electrofishing, and there was research to say, well, look, we know that low pulse rates reduce injury potential in salmonids, so let's reduce the pulse rate, but when we do that, they're harder to catch, so let's fool them and have a low pulse rate of packets, and within a packet we'll have these catching high frequency pulses. So that was the idea behind that, and a lot of these units do have gated burst or pulse trains or CPS, and they go by a number of different names. Okay, so what's drawbacks to pulse direct current? Well, it often does not cause traction, and while that you can generate an infinite number of waveform options, well, that may be an advantage. Is also a disadvantage because folks tend to, if they're not really savvy with their units, they might end up using suboptimal frequency and duty cycle combinations, so they're not using the most optimal pulse direct current waveform they could. Could cause a high rate of trauma, especially in trout and salmon, so that's why the 30 pulses per second or less for trout. And pulse direct current's not as effective as alternating current or AC in very low and very high water conductivity. So what's the fish catching considerations here for pulse direct current? Well, 60 pulses per second or 100 pulses per second, it seems to be optimal for general catch efficiency, and it's also good for, especially 120 pulses per second is more effective for smaller fishes. And if you're using a GPP unit, you need to go with 120 pulses per second so that you can get a robust duty cycle. And we'll talk about duty cycle in a second. Lower frequencies, 30 pulses per second or less, using salmonids, as we mentioned before. Really low frequency, like as around 15 pulses per second for blue and flathead catfish, and moderate conductivity. But it's been found recently that in very high conductivity, over 1,000, like in Virginia rivers near the coast, that this pulsed AC has been found to be effective. So it's low frequency, 15 hertz pulsed DC. And that, there's only one unit model out there, control box that outputs that, but that's been found to be quite effective on blues. Colder water, higher frequencies may be more effective than on blues and flats. Now, that's the frequency part. To the duty cycle part, for general sampling of assemblages, catch efficiency is pretty constant between 20 and 40%. You can go down to 15% without too much loss of efficiency there, but 20 to 40% is a pretty good range. If you can get within 25 to 30%, that's a sweet spot. So a common waveform, 60 pulses per second, 25% duty, that's just a very effective waveform type. As with DC, you can build these volt amp output tables as guidance for settings, given your site water connectivity. Square waves, these square cornered waves, they typically need less power applied for good fishing than rounded waves. And the gated bursts, the last waveform I showed you, they're developed for reducing injury in salmonids while keeping the catch efficiency high. But more power is usually needed even with these gated bursts. But if you have a backpack that'll give you that, you might want to trial that in some streams. Because some folks do like the gated bursts, CPS type pulse trains. Okay, so the next one, next waveform we've talked about pulse direct current and direct current. We're going to talk about the last one, alternating current here, and it should be not PDC but AC up there, alternating current. And we have a sine wave going through there from zero. So we have these positive excursions and negative excursions. And we can go to the peak just like with pulse DC or with DC. We can get a voltage peak, and we can also get a peak-to-peak voltage because you go from the top of the positive pulse to the bottom of the negative pulse. So you get this large swing in voltage. Now those are the peak voltage or peak-to-peak voltage. There's the common way of talking about alternating current is RMS. Root mean square, and that's what, when you say you have 120 volts coming out of your wall socket, they're talking RMS. Now RMS is about 70% of peak power in a true full sine wave. So there's a nice relationship there between RMS and peak. Problem is, electrofishing equipment rarely outputs a sine wave, so that relationship is not valid. Of course, same thing for RMS current, RMS power. There's another aspect of alternating current. Because of these positive, negative voltage swings, there's no constant anode and cathode. They switch places or switch status at the frequency of the generator, 60 times per second. So what's the advantage of AC? It can be effective across a broad conductivity range, and it's more effective than pulse direct current in very low or very high conductivity. And this is because, as we just saw in that last graphic, AC has a higher voltage for low conductivity water, this peak to peak, and it also has a higher current, amp peak to amp peak, for high conductivity water. So it's got more voltage for low, more current for high, so it is for those conductivity extremes, AC is the choice. Now here are some actual outputs, at least the two on the right for electrofishing equipment. On the left, there's a full sine wave, classic sine wave you get out of the wall, which is uncommon. But the Infinity control box, one of the control box models, does put out a full sine wave. You'll see that later in the demonstration. The other two are also AC waveforms. Anytime you have a positive and negative excursion on waveform, it's an AC waveform, but it can take different appearances. Okay, so what are the drawbacks of AC? Well, AC does not cause a traction response at all. There are many AC waveforms as showed you, like triac, AC, nerve, full sine, deviations, and that sort of thing. Many forms are specific to particular models, so this can hinder your fleet standardization because of the various AC waveforms, unless all boats and backpacks have the same control box type. Then you're outputting the same form of AC, and it's possible. Another issue is that most volt and amp meters display RMS voltage or amperage. And that's okay if you have a full sine wave because of that relationship between RMS and peak, because peak is what we really want to get to. But usually a full sine wave is not the form that's being outputted, and thus you don't have that relationship, and you've got to monitor peak voltage or peak amperage with external metering like external scope meters. AC is not available in all models, particularly backpacks. Some backpacks have them, some backpacks don't have AC capability. And AC may cause a high rate of trauma and injury as well. So what are the fish catching considerations? Well, some units have just one form of AC, and others have capacity to change the shape of the AC waveform through changes in duty cycle, actually. And so you're just back really to building volt and amp output goal tables based on a particular form of AC. So just realize that that particular output goal table is based on a particular form of AC. Of course, that's the same for pulse DC as well. And again, you're going to need external metering to monitor volts or amps if you're going to use these volt amp output goal tables with AC. So anyway, looks like we're to the end of that. Thank you.